All right, advanced method, here we go. We've got lesson 3.1.6, and it is symmetry that we're going to be working on today. So the first thing we want to look at is reflectional symmetry. Reflectional symmetry is when we reflect over a line, and then the object just is on top of itself, so the object doesn't change at all. So for instance, let's look at this regular hexagon. If I were to draw a vertical line right through the middle of both of these parts, so here's a vertical line. If I were to reflect over that line, this point would be here, this point would be here, this point would be here. It'd be on top of itself. That is reflectional symmetry. Now, some objects have multiple reflectional symmetry lines that we can make, because I could make a horizontal line right here. And then if I reflected it over this horizontal line, this point's here, this point's here, it's on top of itself again. A crazy thing is this regular hexagon has multiple lines that could work. I've got two so far. Well, I could also reflect over this third line right here. All right, well, what about right here? There's a fourth line that I could use. So I could go this direction and reflect over here, and it'd be the same. Are there any others? Yep. What if I went this direction? Now I've got a fifth line. Are there any others? Yep, from this point to this point. There's another line of reflection. So I've got 6 different lines of reflection that I could reflect this over and the shape would not change. When we get to a kite, it looks like there's only one line of reflection on a kite. If I reflect it going this direction vertically, I can see that this side goes to this side and it's the same object. Now, if I tried to reflect over here, that wouldn't quite work because this point would only be to about right here. It wouldn't get over here. So it looks like that only has one line of reflection where it has symmetry on it. For a rectangle, it looks like I'm going to have 2. If I start here and reflect horizontally right there, this point goes to here, this point goes to here. And if I go right in the middle, it looks like I have some more symmetry. This one goes to here, this one goes to here. It's on top of itself. But if I went diagonal on this one doesn't quite work because remember, you have to go perpendicular. So if I went this line here and went perpendicular, this point would end up being over here, somewhere over here, not over here. So it looks like this just has vertical and horizontal symmetry. All right, so what I want you to do is go through the rest of the shapes and find the ones that have reflectional symmetry on them and draw the line of reflection. I'm going to go ahead and pause and then show you what I came up with. All right, so get to work. Find the ones that have reflectional symmetry. All right, so here's what I got. So it looks like scalene didn't have anything, just a trapezoid didn't have anything. Equilateral had 3 lines. If I went to the vertex up here and then the midpoint over here, it looks like this would work. Vertex to midpoint here, and then vertex to midpoint here because all the sides are the same and all the angles are the same. Square, all the sides are the same, all the angles are the same. So we've got 1, 2, 3, 4 different ones. Isosceles, since this side is the same as this side here, it looks like if I flipped it over from this vertex through the midpoint here, that those would be the same. Circle, so many. I mean, basically any diameter would be a line of reflection. So you could do almost an infinite number of lines there. Rhombus, it looks like if I go through these points here and these points here, I could reflect it. I tried to do it this way, but I can never get it to match up, so diagonally it doesn't really work. Quadrilateral doesn't work. Isosceles, yes, since these two are the same, then that means that if I flip it directly through that vertex angle up there, it would work. Scalene right, couldn't get it to work. Isosceles trapezoid, if I split it right down the middle, because this side's the same and this side's the same. Parallelogram didn't work. And a regular pentagon, I ended up with 1, 2... Oop, I missed one right here. Here's the other one. So it looks like I got 5 different ones that would work on that one. All right, so there's all of our different reflectional symmetry. So it says which triangles are going to give us reflectional symmetry? Well, the equilateral triangle did. The isosceles right did. And just the regular isosceles did. What do all three of these have in common? They have sides that are the same length. So we're only going to get symmetry in triangles if some of the sides have the same length. Quadrilaterals, those are sides with 4. We've got kites. We've got a rectangle. We had a square. We had a rhombus. And an isosceles trapezoid. Now, what did those have in common? Well, all of them had sides that were exactly the same length again. So we had sides that were the same length, and if that happens, then there's possibility for reflectional symmetry, as long as we have some sides that are the same length. All right, which ones have more than 3 lines of symmetry? Well, this regular hexagon has more. It had 6. What else did? That's only 2. That's more than 3. So more than 3. A square had 4 of them. A circle had so many. You can even write them all. And a regular pentagon. Now, what does regular mean? Regular means that all the sides and all the angles are the same. So it would make sense, since we have multiple sides that are the same in a hexagon, this square is a regular quadrilateral because all the sides are the same and all the angles the same. This regular pentagon. So when they have all the sides the same and all the angles the same, you're going to get multiple lines of reflection in it. All right, so that's reflectional symmetry. Rotational symmetry. Rotational symmetry is when you can spin an object on top of itself or spin it and get it on top of itself. Now remember, if we spin, all the way around is 360 degrees. Now we did find in the last lesson that if you spun 360 degrees, obviously the shape is going to be exactly the same because it's going to be just back to its starting point. So when we talk about rotational symmetry, we're looking for something other than 360 degrees. Now this shape here, it looks like it's the same all the way around. And if I go this way and move this point to right here, then this point would have moved to here, and this point would have moved to here. So it looks like if I can go that distance, then I could end up with rotational symmetry. And then if I take this point and go all the way over to this point, then this point would move to here, this point would move up to here, and this point would move all the way over to there. And we'd get rotational symmetry again. Now, how do I know how many degrees I went when I did that? Well, there's actually a way that we can tell. So, if I'm going to rotate this, I'm just doing my center of my rotation to some of these points. Now, a full revolution is 360 degrees. Well, we just split that 360 into 3 parts. This part here, this part here, this part here. They're all the same. So what's 360 divided by 3? 120. So this would be a 120 degree rotation. And then if I went from here to all the way over here, that's 120 plus 120. So that'd be 240 degrees. So there's 2 rotations there that would give us the shape on top of itself. If I went 120, that'd be here to here. and the shape would be on top of itself. You know, if I just spun my paper 120 degrees, there's 120 degrees. See, it's over 90. You can just tell by the angle of my paper it's over 90. And now it's the same shape. If I did another 120 degrees, same shape, but look at my paper. It's not quite back to being up and down. So that's 240 because I did 120 and 120. Now let's do another 120 degrees, 360. And now my paper is in the same spot that it was before. So this shape, I can get two rotations, a 120 degree rotation and a 240 degree rotation where it will have rotational symmetry on it. Now we want to look at this and see which shapes here, if I spin them, are going to give me rotational symmetry. Now we're going to see quite a few of the ones that are in our regular shapes that are going to give us some kind of rotational symmetry. Like if you look at the regular hexagon. So when I rotate, let's say this is point A. If I rotate it here to here, then all the other points would match up, right? Because this one would go to here, this one would rotate to here, this one would rotate to here, and so on and so forth. So if I go that direction, we need to find out how many degrees would that be. Well, there's a way that we can find out. Remember what we did with the last one. We can find out by looking at these angles here. So here to here, how many degrees is that? Well, let's look at all the other rotations that would work. I could move here all the way over to here, and then all the other points would show up. I could move here all the way over to here. So there to there would be this line right here. I could move here and then keep going until I got to this point. And I could go here and go all the way till I got to this point. Now what I've done is I split up my shape into 1, 2, 3, 4, 5, 6 parts. So if going all the way around is 360, if I take 360 and divide by 6, this would be a 60 degree rotation. So here to here is 60 degrees. Here to here is 2 60s, so that's 120. Here to here would be 3 60s, so that'd be 180. 4 60s to get to here, that'd be 240. And then from here all the way over here, that's 300 degrees. And then if I want to go all the way back onto itself, it'd be 360 degrees for that rotation. Okay, so in this one, would I be able to do it? Yeah, if I rotated it 180 degrees. Now, if I did 90 degrees, A would end up way farther down. It'd probably be ended up right over here. So 90 degrees doesn't work. But if I do 180 degrees, A prime would be over here. So a 180 degree rotation would work for that shape. All right, what else? Equilateral triangle. So equilateral triangle is like that first shape that if I rotate it 120 degrees and 240 degrees, it would work. So 120 from this point to this point, that'd be 120 degrees. And then from this point all the way over to here, that'd be 240 degrees. A square, so if I start here at A and I go this direction, if I spin this object 90 degrees, the object's still the same, right? So if I go 90 degrees, it works. So from A to this point, that'd be 90 degrees. If I spin it 1, 2, so 2 90s, that's 180. If I spin it 180, it's the same. And if I spin it 270, it'd be the same. 270. Then we get the same. Now what about 45 degrees? 45 degrees, is that the same? No, now it's a diamond shape, right? So that doesn't work. The next shape that would work would be a circle. Yeah. So I can spin a circle however I want. So any degrees. No matter how many degrees I spin that circle around the center, it's going to be the same. So we got that one. A rhombus. If I spin a rhombus, let's see if I spin it 90 degrees. Does that work? No, that's not the same shape. But if I spin it 180 degrees, yes, that is the same shape. So a rhombus, we could rotate it 180 degrees and it'd be the same shape. Isosceles triangle. 90? Nope. 180? Nope. Okay, it doesn't look like that one works. Let's see, what else do we have? Let's see, a parallelogram. Let's try to spin this one 90 degrees. No, that's not the same shape. What if I spun it 180 degrees? Ah, that is the same shape. See, this is the same thing as that. So 180 degrees rotation does work for this one. Ooh, the tricky one. Pentagon. Now, I know that I can spin it because if I just spin it right to here, it's facing up, right? And it's the exact same shape. If I spin it here, well, that part's the top part, and it looks like the same shape. If I spin it to here, spin it to here, spin it back. Oh, looks like I spun it 5 times. So it looks like these are the angles that I could spin it. Can you figure out how many degrees we're spinning it when we do that? Now think about it. There's 360 degrees total. And look at how many times that we're spinning it. Well, in order for this to work, we do it by 72, because 360 divided by 5 would be 72 degrees. So spinning here to here would be 72 degrees. Another 72 would be 144. So here to here is 72, here to here is 144, here to all the way over here would be another 72, so that'd be 216. So that's here all the way to here. Our last one would be 216 plus 72, which would end up being 288. So those are all the rotations that would get that onto itself. All right. Next part, translation symmetry. So translation symmetry is when we take a shape, remember, and we move it right or left or up and down, and then we say, okay, is it going to be the same? Well, all of these shapes, if I start moving them, they're not going to be on top of each other. Like if I move this one to the right, it's not going to be on top of itself. If I move it up, it's not going to be on top of itself. So none of these shapes have translation symmetry, because translation is just where we move it up and down, left and right. So do any of those shapes have translation symmetry? No, they do not. Now, could we make something that has translation symmetry? Yes, we can. Lines. If I've got a coordinate plane, and let's say I've got a line and it starts here at 1 and then it goes up 1 and over 1. So lines go forever, right? Now if I translate this line, so if I take this point and I say, okay, I want to translate it right 1 and up 1. If I take this point and go right 1, up 1, it's on top of itself. This point would go right 1, up 1. This point back here would go right 1, up 1. This point here, right 1, up 1. So translating all the points on that line would just put the line on top of itself. So if we've got a line and we translate it the same as the slope, then the line's just sitting on top of each other. So lines that are translated according to their slope have translation symmetry. All right, symmetry of a decagon. This is 10 sides. Now we should have seen some kind of pattern happening here. When we had a hexagon, its reflectional symmetry, there were 6 different lines of reflection. When we had a square, there were 4 different lines of reflection. When we had a regular pentagon, there were 5 different lines of reflection. So what we should see here is there should be 10 lines of reflection. Now, where are those 10? Well, 5 go through the angles. And 5 go through midpoints. So what I'm saying is if I go angle to angle, that would be our line of reflection. So there's one of them, and then I'd get 4 more. This angle to this angle, this angle to this angle, this angle to this angle, and this one to that one. So I'd get 4 going through the angles, and then I'd get another 5 going through the midpoints. So midpoint, so if this is the midpoint and this is the midpoint, there I get another one. So anytime you have an even number of sides, which we do in a decagon, you're going to get one line of reflection for half of the angles, because when you do an angle, they match up there. And then another line of reflection through the midpoints of each side. So we get 10 lines of reflection. Now let's think about the rotational symmetry of this one. In the rotational symmetry, what did we do with all these objects that were regular? Well, what we did is we looked for the angles and we said, okay, I can move this one over to here, and then I can move that one to here, and that one to here, and that one to here, and that one move over to here. This one spin it all the way over to here. This one spin it over to here, and so on and so forth. So how many of these little pie shapes would I end up with in a decagon, a 10-sided object? Well, I should have 10 of them. So a circle going all the way around is 360. If I divide by 10, that means that every 36 degrees, I should get rotational symmetry. So 36 degrees, 72 degrees, 108 degrees. Oops, that's an 8. So we should see rotational symmetry every 36 degrees, because it's 360 divided by the number of sides, which would be 36. All right, moving on. We're almost done. All right, decides which graphs have reflectional symmetry and which graphs have rotational symmetry, and if any of them have translational symmetry, or a combination of those 3. I want you to look at them. I'm going to pause it real quick, and then I'll show you my answer. All right, so the first one, it looks like we would have rotational symmetry. Depends on where I rotated it, but if I rotated like around this point and then started spinning my paper, it'd be the same exact line, right? If I move it to 180 degrees, just around that one point, so that would work. Then I've got translation symmetry. If I move this point up and then to here, all the other points would move up and over to here, up and over to here, so it'd be on the line. Reflectional symmetry, if I reflected over, remember, a perpendicular line? So if I reflect over this perpendicular line, these points over here would be on this side, and these points over there would be on that side. Reflection for this one, if I reflected right on the y-axis, this side would be the same as this one. For this one, if I rotate it 180 degrees, whoa, we see that it's the same shape. And this one, if I translate this one this direction, this distance, So it looks like a distance of 1, 2, 3, 4. If I go a distance of 4, this points to here, and this points to here, all the points end up matching up. So that one has translation and rotation. This one, if I were to reflect it diagonally right here, so I can see that this one would go across and meet up with it. And if I rotate it 180 degrees, it would be the same. Okay, this one, if I rotated 180 degrees, it would work. And if I translated it up and then to the right, this point would end up here. And then up and to the right, this point would end up here. So the points end up matching up if I translate up and right. Last one, reflectional symmetry. If we reflect over the y-axis, that would work as well. This is just a little bit of a bonus. Anything that if you reflect it over the y-axis, it has a symmetry over the y-axis. We call those functions as even functions. So we do have a couple of even functions. Number 2 and number 6 we would call even functions because they have a line of symmetry that's the y-axis. So that'd be 2 and 6. Odd functions, we refer to those that if they have rotational symmetry at the origin. And we actually did have 3 and 4. They were able to be rotated about the origin. This one, if we spun it about the origin 180 degrees, it was the same. And this one, if you spin it about the origin 180 degrees, it's the same. And we would call those odd functions. That comes up much later in math. But even function would be across the y-axis symmetry, and the rotational about the origin would be an odd function. All right, so we've got methods and meanings for this part. And this one just talks about parallel lines and perpendicular lines, which we've already covered before. But if you've forgotten what it means, parallel lines have the same slope. Perpendicular lines have opposite reciprocal slopes. So this just goes back over that. There will be stuff on the homework about this. That's all I got. Be good.